BKW Physics. I'm Mr. McConley. We're going to talk about fusion today. So, previously we talked about fission. And fission is when you took a large nucleus and you split it. And when you split it, there was a discrepancy between the total mass on this side and the total mass on this side, which was called the mass defect. We're going to use that same concept when we talk about fusion. Let me give you an example to start things off. If you had 2,1H and 3,1H, the product of those would be a 4,2 helium and a neutron. Now by itself that looks very mundane and simple, but if you know what's happening here, you would realize, in fact, back up before I even say that. On the top here, we add up and we got 5. On the bottom, we add up and we got 2. You look at this side, top, we add up, we got 5. Bottom, we add up and we got 2. So you look at it and you say, oh, balanced, good, we're all set. But I wouldn't be showing it to you if there were not a little bit more to it. Because when you actually add this up in detail, like you carry it way out, point, and you carry it out, it does not add up. It does not add up at all. It's pretty far off. And in fact, in order to make that balance, or that, so that these two sides are actually equal because of the mass defect, and remember we're overcoming what's called binding energy. It's kind of a review. I've already thrown these terms out. I'm just throwing them down again for your benefit, so it reminds you. How much do we need to balance this equation? Well, it actually turns out to be 17.6 mega electron volts. So to make this balance, we have to have 17.6 mega electron volts, which the way I wrote it last time is I wrote this as a big capital Q, which you could do the same. Basically, you need energy to make this thing balance out, and that energy comes in the form of heat. Fine. So, you got this set up here, 17.6 mega electron volts. Let's kind of put our minds around what that means. Dynamite. Everyone thinks dynamite's impressive. You can blow stuff up. It's very strong. Well, one dynamite molecule produces 20 electron volts of energy. What's this? What's that number? This reaction right here is 17.6, but that's mega, so that's 1, 2, 3, 4, 5, 6. That's 17,600,000 electron volts. So if you're comparing dynamite to this fusion reaction, dynamite's a joke. Okay? In comparison, per molecule, dynamite's an absolute joke. That gives you some frame of reference how powerful this is. Now, where do you see a fusion reaction? Because we don't have fusion reactors. Like, we don't have nuclear power plants that run on fusion. Well, there's 2 places I can think of. Do you have one, Chase?
The sun.
The sun. The sun is a fusion reaction, which constantly is producing helium. It produces so much heat energy that it's unfathomable, and luckily we're such a large distance away that it doesn't just melt us right down. There's another example, though. We've used this in other ways. You know? Where? When? Well, yeah?
Atomic bombs.
Yeah. An H-bomb. H-bomb. Atomic bomb. We know how to make this happen here on Earth. We can make this reaction, this fusion reaction, happen. Problem is, we don't have a way to make it happen and control it. Like with fission, we learned that we can use control rods and moderators and things like that. We can keep it moving forward at a reasonable pace and still reap the benefits of all the heat energy. This reaction, we don't have a way to do that yet. We start it, it's like, ooh, it gets really hot really fast, and ooh, and it's over. And That's great for a bomb. It works well for a bomb. You just boom, you let it go, and away she goes. But that doesn't work good if you're trying to harness that energy because it happens too fast, too much all at once. That's where we're at with fusion. Another example is a tokamak reactor, but again, it's a very fast burst of energy. So for today, that's physics.